Every digital mode on high frequency asks you to take the channel, use it, and then give it back, just like a phone call. mLink asks a different question. What if we just treated it like a normal amateur net, like the Maritime Mobile Net? One thing before we start. The slides have a lot more information than I will say verbally, so feel free to pause or come back as needed. In the past, we built our digital modes like telephone calls. We have 2 stations, a session that belongs to that link, and a beginning and an end. But that's not how any of us actually operate on a net. Nobody runs a net by taking their traffic off to another frequency and then forget it afterwards. On a net, everyone listens and everyone keeps a log, at least mentally. The whole difference is where the memory of the content lives, the message you're actually sending. If we sort digital modes 2 ways, if it talks to one station or we're talking to everybody, and the other axis, does it remember anything? mLink and Packdoor do remember messages because we have the CMS, and Packdoor itself has some forms of forwarding, I think, in their protocol, but only 2 stations may speak at once. FT8 and APRS let everyone speak on a shared channel, but nothing is remembered and nothing is delivered. The corner where a broadcast has a memory is simply empty, and that's where I built mLink, and that's the corner mLink is built in. That empty corner is not a curiosity, it's where the cost is. When one exchange owns the channel, every other station is paying for it in time they'll never get back. This is a real capture of an mLink transaction over a simulated radio link. Time runs across the horizontal axis and frequency is on the vertical, and those small rectangular marks along the bottom are stations on the shared channel announcing themselves and reserving the channel, and the big wide block at the top is a single bulk transfer. It's OFDM, and the block after it on the right is the retransmit of the few frames that were intentionally lost in this test. Everybody on this frequency saw all of it. So if you were sitting here and on the mLink channel with mLink running, all these messages would be saved to your local station, and you could relay them, or you could upload them to the CMS once it's complete. There's no calling channel, and there's nothing to tune to. You just sit there and you listen and you speak when needed. Almost nothing here is new. The contribution is the selection of us taking what has been learned over the last 50 plus years of radio theory and protocols and putting it into something that's useful for the emergency management. Each one of these things did something extremely right, and each of them is still on the air today because of it. But here's the part that matters a little bit more, is what we declined to take. mLink got the product itself right, and it got it right about 30 years ago. Mail is definitely the correct unit for emergency traffic, and everybody expects that, and there's not really a problem with the mail itself. And also, it got right the global store reachable through the internet gateways, and that is an excellent, correct topology, especially whenever it becomes more of a managed communication like this, a managed, distributed communication. The exclusive session, though, was never the idea of mLink, as far as you contact one station like a telephone call, but it was a constraint that ended up having decades of it's a constraint. So if we look at the entire task of sending a message and doing emergency management and sort of apply the OSI layer to it, high frequency itself as a physical medium has no network layer. It's not like a router where, you send Ethernet packets somewhere and there's already these concepts of routing and all that. That all has to be created itself. And for most protocols that have existed in the past, there isn't anything like that. There's no real OSI model with networking. There is some routing, but all that ends up happening into the application layer. And then you're kind of stuck in this sort of hell where where your application has to do everything. Now, that's not saying mLink's much different from a practical perspective, because it is one program, but because of the way that I've segmented out the different layers of mLink, it all works very cleanly together like you might expect it to. And most people expect a modem to just be handed just bytes, and then it does something with those bytes, and you get bytes in and bytes out like RDOP does. But the thing is like you can't really arbitrate a shared channel with that. You can't really do automated forwarding or delivery. All that has to exist on the application layer, and that means that you get really, really inefficient usage of airtime if you don't have all these layers that where the protocol itself knows what the application wants. A benefit of giving each of these individual jobs a layer of its own in our little fake OSI model is that a whole category of work quietly stops being the operator's problem, such as figuring out which stations to hop to in order to route a message, a problem of trying to dial a bunch of stations in the hope that one is listening somewhere and reachable that you can get to, because everybody's already on the same frequency for that band, and you don't need to change frequency within the band in order to be able to find a station. You don't need to know their call sign. You just need to either put your message out there and somebody will pick it up, or because you've also been sitting on the frequency and listening for a while, you already know what other stations are there, and you already know which ones are connected to the internet and can deliver your message. And the operator doesn't have to do this routing mentally in their mind or in a notebook, because mLink as a protocol already handles it. Here's the hinge the entire design turns on. If being more robust can cost you seconds, which it does, then you're forced to hunt for the fastest rate that the link quality will bear. When you hunt for this and you do this, it means that you have to negotiate it, and almost every single protocol out there does this. VARA does it, Pactor does it, RDOP does it, trying to find the fastest, most widest bandwidth that the link will bear. And during that time, you're going to have a lot of repeats. You're going to have a lot of figuring out and sounding and figuring out what the link quality is. And so with mLink, what we did is instead of having these negotiations cost the very seconds that we're trying to save by being faster on the band, what we do differently is we choose robustness first by design. So that way you have to spend less total time transmitting, and then because it's also concurrent, you can have multiple transfers going on at the same time. And that's not saying mLink is slow. mLink is pretty darn fast for the amount of bandwidth that it takes because of our high use of compression and our really good decoders. And so that's why we're able to get bulk really fast traffic, 600 and about 600 bytes in about 5.5 seconds, decoded in just 5.5 seconds. That's really fast, while other transfers are going on at 0 dB with additive white Gaussian noise. So that performance is nothing to scoff at. And because the real benefit though comes from the concurrent and asynchronous nature of the communication protocol that allows these things to have less total wasted time on air. So since we never negotiate, but we still want to be as fast as possible, instead what we do is we keep all of our bulk frames the exact same length and modulation scheme, so it's robust by default. But what we do is we change our encoding rate so that way we can fit more bytes into the same amount of time if the link quality allows it. And we do it in a way that's conservative enough to where we get most of our message through on the first try every single time. And when we retransmit, we do a differential transmit of what actual bytes we're missing from the message. So it ends up being an extremely efficient way to, by default, get a message through. So even though with our most robust setting, we can decode reliably down to 0 decibels and even down to -1, if this fails, it's not a signal to us that we need to try harder and just try again to continue to transmit, because there's more than one person, hopefully on the frequency, it's a signal that this path is wrong, and we need to go ask somebody else to go ahead and take our message for us. These here are actual measurements, and they're not estimates, and they come out of my test suite. And the suite pulls all 5 signals out of one block of noisy audio at the exact same time. So we're decoding all 5 individual signals that mLink supports simultaneously, picking them out of the baseband with our detector and decoding them. And that's the job of our receiver, and how to correlate them together is the job of our Mac. So because we made it in these layers, it makes it really straightforward in how to deal with it. But down at the bottom of that scale, a station you could not hear at all is still delivering traffic in the net itself, because we have knowledge of second order links, because each station will opportunistically, whenever it announces itself, it'll also announce a couple stations that it hears. So that way there is a node graph being built of who can hear who dynamically just by being on the channel. mLink supports 3 main data transport arrangements or structures, not necessarily a frame, because we have generally 3 different primitives or frames. We just string them together. So for example, on the announce band, what we do in order to get messages across, instead of having a frame that might be long and encode like some data in it, what we do is we have a family of frames, and then each one has a meaning, and then depending upon what the next subsequent frame series are, we have a string of announce frames that mean something else. So we can kind of use the order of the frames as an additional layer of it to increase the encoding efficiency and value. But as far as transferring bulk data like mail and frames and weather reports and things like that, we have the short burst, the long burst, and then the bulk transfer. The bulk transfer is covered quite a bit in this presentation, but the short burst is basically just taking some announce frames and then just stringing that data together, and it still gets the same differential acknowledgement protection and the differential retransmit. And then the long burst is just multiple short bursts, so we can fill that gap between, hey, we only need to send a message that's 50 bytes long versus, the maximum value of a bulk transfer, which is about 600. The minimum maximum is about 600 bytes. We don't want to spend 5 seconds whenever we could spend, 1.5 seconds on one of 3 announce channels. The only kind of middle ground is the long burst. And the long burst really shouldn't be used very often. The only reason that should be used is if you literally can have no other way of getting a radio-to-radio message to that other station. And so you would string multiple short bursts together to get about up to the capacity of a single bulk message. mLink's maximum payload compressed is under 64 kilobytes. Under 64 kilobytes for the maximum compressed payload, which means that your maximum sent payload actually is determined by how efficient the compressor is. And that is queued every time that you draft a message, and it'll tell you whether or not you have a big or small enough message. The robustness of mLink also costs bytes, because we use, of course, Reed-Solomon encoding, and that costs about a 50% overhead for short messages. And for our most robust LDPC rate for our bulk frames, that also costs 50% overhead. And so we have to find a way to buy those bytes back so we can still be fast. And we do that through really, really aggressive compression. So we can always make more dictionaries based upon what type of traffic that mLink transfers. And the more that mLink is used and we get real message traffic, the better our compression and the faster that mLink can become. But in our small example that I did for compression, we had a 118 character message, and if you just put it with a default compression algorithm, it's really too small for a compressor to find anything usable to work with to actually make it smaller. So since we use ZSTD, we can use something called a dictionary to be able, if we know kind of the general shape of the traffic that we're going to be sending, we're able to compress very small bits of text even smaller. So since we already know what ham radio generally sounds like, we can recover, we can compress that data a lot further with the use of dictionaries. So every round trip on high frequency costs seconds that you can never recover. And this is also from keying delay and the receiver, maybe having a little bit of a delay in it between the time you actually decide to send the message and whenever you get it back. And that churn can add up extremely quickly. So we want to do as little of that as possible. So the rule that I applied like from the very beginning as a fundamental rule of mLink is that, and we applied it everywhere that it could possibly go, is that if a station can hear the answer, we don't need to ask the question. We can use the structure of the protocol itself to infer and share relevant information as much as we want and be able to really increase the density of the amount of useful information that the operator actually needs to know and to help the operator do their job as possible. But what something does eventually fail, because it's HF, of course it is, the cheapest thing you can possibly send is the bytes that only were missing and nothing else. And our protocol really does this very smartly, and I'm kind of proud of it. We don't repeat the individual frame that carried them. So if you're missing frame 4 and frame 4 was whatever, you resend the frame. We take in the burst of information that we send, we know which bytes never made it there, because we know which frame carried which index and how many bytes. So whenever we retransmit only what was missing, and then we cap our transmission, we cap the error correction rate to the one that was last most reliable. So that way we have a much lower chance of repeating ourselves again and again and again, because that churn is again lost time. And if nobody answers at all whenever we try to get those missing frames, then or resend those missing frames, and that's not actually a lost frame, it's a lost station, and shouting louder won't find them, so we just need to transfer it to somebody else to take that message, possibly put it in the CMS, and then that other station that we were trying to send to will pick it back up whenever they rejoin the network. One of the constraints that we really had as far as targeting the amateur service is the 3 kilohertz passband of your normal sideband transceiver. And if you look at this graph here, it really doesn't take that much room to do all of this, all the routing and concurrency and the speed rate. We're just smart, trying to be as smart and as efficient as possible with it. Right now, mLink does not have a band plan. There's no frequency that I've proposed at all to where this frequency on this band is the mLink channel, to where you tune to that, much like we have for SSTV and we have for the Maritime Mobile Net. That's fine. And a consequence of that is somebody might ask when they're introduced to mLink is, well, what about, can I run this on my hand transceiver via a DigiRig mobile or something like that? And although the answer is yes, you have to have single sideband on whatever transceiver you use, which is a lot of people may not like. And I actually talked to a friend of mine, Peter LaRue, about this, who I worked with RDOP with. But of course, there's a problem whenever you get to frequency modulation, that most of these hand transceivers and that is accepted as standard on the VHF and UHF frequencies, they tend to like FM. Because the current mLink implementation needs a linear channel like a single sideband where you could just put energy wherever you like in the band, and there's no actual carrier. With FM, I'm sure with FM, the discriminator is gonna lock onto the strongest carrier, and everything else will get wiped out. So you cannot have true concurrency with frequency modulated baseband, unless, of course, literally you have control over the synchronization of the deviation of the FM transceivers, which we do not. We operate on basically just sending audio samples to the device and then having it to do whichever mode that's configured for. And mLink is a single sideband, so in order to implement something like this, it would basically be I assume, because I've never used Vara FM personally, it'd be just OFDM in a time multiplex and not also a frequency multiplex. And so we wouldn't have as many of the benefits of mLink as a total protocol, but you would get faster data rates, and it could also just be one unified interface. So something that to consider that has not been built and honestly wasn't even addressed until a week ago whenever I emailed my friend. Here we have another render of our actual simulated mLink channel. And you can see here it shows two stations begin transmitting to a third on two different announce channels. And their transmissions overlap in time, but that's no problem for the receiver. And the receiver is able to pick those apart and end up associating them with each other properly. And you can receive a lot of information from many stations all at once. Neither one had to wait. They just had to simply not collide with each other. And we've got a nice anti-collision set of rules that really help with that. Of course, it can happen because you can't listen when you transmit, at least with most of this hardware. And so, this is as good as you can pretty much get without going ahead and implementing a net controller type feature, which I've explored, but this would be a conversation to have with RSFI with whether or not we want to have a more structured channel to where at the top of every, period, like say 5 minutes, there's a roll call from a net controller that can hear. I've already built a lot of that, but it's not really, it's more of an enhancement, and I haven't really decided whether or not I want to do that yet, but that's an option as well, an idea if you care. Now back to memory, the piece that turns a mode like mLink into an actual network. An individual station doesn't decide what to remember based on who the traffic was addressed to. All addressing does is whether or not you're notified of it. So mLink will remember everything that it hears, and it can go ahead and fetch messages for somebody's mailbox for them as well. And then that can get stored and relayed if possible. And stations, if they know something is addressed to them, they can actually ask another station, hey, I heard that this message was for me, but I couldn't have it. And any station that has it in their messages table can go ahead and give it to that station that's missing it. A nice byproduct of the second-hand links from the hello, which I mentioned earlier, is that nobody has to publish a map of where people are and who's who, because the map ends up assembling itself out of things the stations were going to transmit anyways, and that we can infer just based upon the traffic with decent certainty. When it comes to relaying and multi-hop is actually just emergent out of the way that mLink handles traffic, because at least for in this example here, we've got digipeaters with APRS. The operator has to type or select a path into the frame and then just hopes that that network still exists there. But here, whenever we want a relay, the question goes out, hey, can somebody relay this for me? And then we get answers back from other stations, or that they self-volunteer based upon their knowledge of their link quality to that station. And then the relay basically is never configured, or it never has to be configured by the operator. The stations themselves, because of the protocol supports it from the ground up, volunteer it, and then you just get your mail. And then multi-hop, which I know for many protocols can be really annoying to set up because everybody has to be participating in at their stations, or their station has to be set up for it, and the configuration is not fun. mLink just does it. Nobody planned this route. Nobody even knew it existed because it built itself based upon the each station building knowledge of the network topology through just listening to it and listening to stations announcing themselves and knowing who can talk to who. In mLink, much like many other protocols, we have a couple distinctions of the consequences that come from your station capabilities. The main thing that really matters is whether you have internet or not, and whether or not you're attended or not, as in like there's a person there at your station immediately to handle traffic. And also how good your link is to the next station. But the thing is with mLink is that nobody actually configures all of it. All of it mostly, except for your presence at the station, comes from your station characteristics. And the point is to get the message out to the CMS generally as much as you can. Of course, you can just do peer-to-peer just fine. And if the two nodes in the network through their peers can hear each other through a relay, then mail will just get there. But if not, it'll just hold as deferred. And then if you hear an internet connected station, which acts as a gateway, any station can act as a gateway, it'll just deposit to the CMS into that operator's mailbox. And whenever they connect back to the network, or they pop on, or they hear another station with network access and they request mail, they can get their mail without having to dial anybody in specific. So once we have a network that moves messages instead of making and starting and stopping connections with content in the connections, the address stops needing to be a call sign. It stops needing to be another station. It can be a subject. It can be an agency. It can even be a shape that you drew on a map. Think of kind of like a mailing list. That is kind of what it can be like. And that can be really useful for search and rescue operators. This is the interface that an operator would actually see when working with mLink. I like the Windows 95-esque kind of theming. It's clean and it works. So it's not a modem window, and it's not a command line terminal. It's a workstation that has all these applets that do the things that you need. So everything an emergency operator would reach for, it goes here in one place. And if you need another function, we just write another applet, and it's all driven by a single process sitting either at the radio or even remote, because the front end and the modem itself are separate processes, so you can connect over a network, or the operator console could even run in the web browser. So operators don't even necessarily need to install the software onto their local system if they can at least at some point reach a website that holds the client. So updating and distribution becomes as simple as just pointing the browser at a URL, and then you have the most up-to-date client. One of the big focuses on the development of mLink is having a really nice map. And we actually draw the link table directly on it. So whenever you hear a station, the station will pop up on the map, and you can see the link that it has between other stations. And it's nice for the operator to see who's who and where's where. And also you can draw things directly on the map and then send those points of interest or the map datum to others just as a regular old mail attachment, including to those topic lists such as an agency, an organization, or a mission. One thing that is proved to be somewhat of more of an administrative and a design challenge, and one of the reasons why I chose now to reach out to RSFI, is because WinLink doesn't really have a single customer for its mail stack. It's got at least 4, and they all want slightly different things. Boat in the middle of the ocean has no infrastructure, and an emergency manager needs their forms and accountability for things. And we support most WinLink forms in mLink. I've got a parser for that. And then Mars and shares operate on federal frequencies where encryption is expected, and we support encryption if you're an authorized station. And on the amateur bands, obscuring a message is illegal, so you can't use encryption there, of course. But one stack, mLink serves all four because what separates them isn't the radio. It's the way that it was developed in an OSI-like model, and then also which certificate our certificate authority has decided to issue you. So I need to be really plain about encryption because it's the first thing that anybody, at least for me when I started developing this, anybody's asking about. mLink definitely encrypts, and we use public key infrastructure and also support pre-shared keys. So a relay, what's kind of cool is that a relay can carry a message even if it's not permitted to read it, because the message tables are stored in blobs in the mLink database, and it can know basically where it needs to go, but the actual content of it, it doesn't. So if you've got one channel that you're using for federal purposes, but you've got different consumers of those messages, then you can easily get the benefit of the mLink routing without needing to be able to peek into the message. Of course, on the amateur bands, we turn that off because obscuring, it's illegal. And it's also not something that a clever operator can just turn back on easily. I mean, you can just hack the software, of course, but it's not just easy. What determines it is an administrative thing. Somebody from mLink has to give you a certificate that's signed in order for it to work, or we'd most likely defer certificate issuance to the organizations such as Mars and shares that can manage their own certificates for their own organizations. Dealing with mail authentication is like B2F does it a certain way, but I really wanted to reduce the churn of just sending back 4 or 5 bytes at a time, which really would slow mLink down really bad. So I had to choose a little bit different of a way. And obviously there's some issues with registering a mail over the air, because the first person who ends up claiming a call sign is going to get it, pretty much. And we can't just send passwords over the air because then anybody else can get it. And the challenge response of B2F is not going to work for being efficient on the air. So we've got a kind of a big design problem. And this is open to change, but currently how we do it is that since radio is public, we don't want to send passwords over the air. And any proof of a password that crosses it can be captured and then attacked at leisure, such as even if we hash it. So there's no clear password here that we use at all. The only password that ever gets used is whenever you connect to the CMS to claim your device. So how we do it is 2 public keys pass each other in the clear, where anyone is welcome to copy them, and both ends independently arrive at the same secret on each end. And the gateway that relayed the whole exchange learns nothing from this, and they cannot impersonate or say that a message came from you, or say that it came from somebody else, or change the content of your message without it being rejected by the CMS. So the entire point of this is to make sure that nothing that enters the CMS is ever not actually from the original sender. We can't control realistically, I mean we can, but we can't realistically control and authenticate and sign every single message that goes in between each and every operator over RF, because the overhead is really high. And there's no real reason to do that anyway, because at least in amateur radio, we still have a pretty good professionalism and a trust model that even when you're on a regular voice net, is that you're not generally going to have a person get on the radio and then use a fake call sign and impersonate somebody else. I'm not saying it doesn't happen, but that's the trust model that we have here. And this is also open to discussion. So I'd mentioned the tension of the relay before, is because we don't have individual trusted gateways like WinLink does. We have opportunistic gateways by anybody who volunteers to be a depositor to the CMS and has an internet connection. We want to make sure that whatever station that may carry the mail, we want to make sure that if that station delivers it to the CMS, that it is the person who wrote it. So we call this person a courier, And what stops the courier from changing the name on the envelope or changing the content to your message is a light mail signing. So we use a key that both the server and use the CMS server and you have, and we tack on 2 bytes on the end. That's a hash of the message and basically your private key. And now for proper signing for something like this, normally it would take many bytes that would take up most of the message. So instead of using a real signature, we just use 2 bytes that gives something like a 1 in 65,000 chance of guessing it. But just due to rate limiting and the fact that you only would use these message bytes over the air, the ability to attack this and luckily guess would be really low, and we would end up probably just blocking from that host at some point if they were intentionally trying to impersonate or deliver malicious traffic. In the project itself, it's nothing exotic, kind of like Codec 2 is kind of a pain in the butt to build because it's got CMake and a bunch of other dependencies. mLink is C. It's C11 because we needed atomics. We vendor SQLite 3 as a database, Z STD for a compressor, and embed TLS as bundled dependencies. So for it to run on a system, all you have to do is compile it. RDOP taught me that was the way to do it, and it runs on pretty old hardware because my compressor and my FFT algorithms are pretty efficient, and so I've tested it on 15-year-old laptop, but it could probably run on a Raspberry Pi or just about anything as long as you don't end up underrunning your buffer. And so for this entire pitch of trying to get AirSFI to sponsor me to do this work and perhaps a funding grant so I can get paid to do it, that would be really cool, is by working with AirSFI that helps me understand and better meet the needs of AirSFI's customers. So the hard engineering, the modulation, the error correction, how the protocol and the modem itself works, how the entire technology stack works and is tested and all that has already taken a year and a half of me working on it, several days, every single week. But the hard administrative things, somebody has to decide how an organization runs its own certificate authority, because it'd be a mistake for that to all run through mLink administrators. It's too much work. And then somebody has to decide who is allowed to say that a call sign belongs to whom. And right now we just have a trust model of the first come, first serve, but there's probably a better way to do it. And I don't have the experience of running a large data system like WinLink CMS does. So I'm hoping that you guys will see the value in the work and the protocol and the reliability and see that mLink, how I do it here, is the future of emergency management on HF with amateur radio, and we could work together. The implementation question is largely answered, but the product question is AirSFI's, and I'd much rather build it together than beside you, and then it's not ideal. So thank you for listening to this pitch, and hope to hear from you soon.